Hi, so today you are going to see potential distribution across the insulator string, namely we will call it as string efficiency. So first of all, you must know what is potential distribution over insulator string. So generally in transmission system, high voltage transmission line systems, so we have a insulator strings which is used to hold the high voltage conductors. So there will be a potential distribution across the string. So it will be equally distributed, depends on the connection. So general structure. So insulator strings. So normally it is a made of porcelain disc. So which is used to share the electrostatic stress across the string. So here we have the conductor which is holding nearer to the line conductor, and we have 3 discs over it. So normally if there is a porcelain disc which is connected between 2 metal links, it forms a capacitor. So there we can say that there is a capacitor. So if there is no this capacitor, what do you call it as? Self capacitance or mutual capacitance. Suppose if you are going for the effect of shunt element, so this is your 3 disc insulator porcelain disc, and if you are considering the effect of shunt capacitance, normally 2 parallel plates separated by a dielectric medium, we will be calling it as capacitance. So here this insulator disc normally made of porcelain and which is connected between 2 metal links. So it is connected through 2 metal links and it is joined together. So which forms a capacitance called self capacitance or mutual capacitance. Suppose if you are considering the effect of tower, there will be an shunt capacitance effect. So between the metal links and the tower, so there is one more capacitance exists. So which is called shunt capacitance. So the capacitance exists between the insulator disc, metal links and the tower, which is called shunt capacitance. If you have only the effect of self capacitance, then the voltage distribution will be same. So the current flowing through the conductor is same. The voltage distribution across the strings are same. So the electrostatic stress, it is equally distributed over the insulator strings. Whereas if you are considering the effect of shunt capacitance, your voltage distribution will not be same, it is different. So because of the effect of shunt capacitance. So now you are going to see what is the string, what do you mean by string efficiency. While considering the effect of shunt capacitance over here, so the voltage distribution across the conductor, nearby the conductor, will be having higher stress. So the voltage disc, the porcelain disc which is placed nearer to the conductor, will be under high stress. Whereas if you are going away from the conductor, it is getting reduced. So for example, if you are going for consideration of shunt capacitance, how it will look like. So this is my self capacitance and this is my conductor. So I am just naming the self capacitance as C. So if this is the case, only self capacitance, you have the current is same as I. While considering the effect of shunt capacitance, named as C1. So this is my tower support, the effect of shunt capacitance. So if this is the case, the voltage distribution is not same. So we are going to calculate what are all the what is the voltage distribution across each insulator disc. For example, here we will be considering the effect of current flow. by I1 dash, I2 dash, I1 dash. So, at each junction point you have to apply KCL and we have to calculate the effect of what is the voltage distributed across each string. So, before getting into that, you must know what is meant by string efficiency. So, string efficiency is given by total voltage across the string divided by number of discs into voltage across the conductor, voltage across the disc nearer to the conductor. So, it is given by voltage, total voltage across the string divided by number of disc into voltage across the disc nearer to the conductor. So, now for example, we are going to see a problem in a 33 kV system. There are 3 units. There are 3 units in the string of insulator. If the capacitance between each conductor if the capacitance between each conductor, pin and earth is 11% of self capacitance, of each conductor, then find number 1 voltage distribution over 3 insulators. Number 2 string efficiency. So, here in this problem it is clearly shows that it is given with 33 kV system, there are 3 units. So, we have to draw 3 insulator discs. So, we will have 3 capacitance and this is my support, right. So, it is given with 3 insulators and if the capacitance between each insulator pin and earth is 11% of self capacitance. Pin and earth means it is your shunt capacitance. So, we have a short form called the term K, which is given by ratio of shunt capacitance to the self capacitance. So, here the value of K is given here. The ratio of shunt capacitance to the self capacitance is given as 11%. So, which means it is given by 0.11. And total voltage across the string total voltage across the string is given here as 33 kV. Since this is line voltage, for calculation you can convert that into phase voltage. So 33 into 10 power 3 divided by root 3. So convert into phase voltage. So it is 19.05 kilovolt, right? Next thing is, you have to consider the effect of shunt capacitance. So self capacitance is named as C, and voltage distribution across each string, it is V1, V2, V3, and this is the total voltage V. So what is your effect of shunt capacitance? From this K, the shunt capacitance is K times of self capacitance. So it is K into C. The K value is given. So it is termed as K into C. Now we have to assume the current flow, and this is my conductor. The current is assumed here, which is I3. So all self capacitance current is taken as capital I, and shunt current as small I, small I1, small I2. So now what you have to do? So at each junction you have to apply Kirchhoff's current law. At junction 1, so you can take junction 1 and 2, or just name it as AB. You can take at junction A. At junction A, you have to apply your KCL. So I2 is the incoming current. I2, capital I2 is equal to capital I1 plus small I1. Yes, capital I2 equal to capital I1 plus small I1. So write your current in terms of voltage. So how will you write? For example, here we have current I2 which is flowing through the shunt branch over here. The voltage across this I2, that is capacitance, is V2. So how will you write in terms of voltage? It is V2 omega C is equal to V1. I1 is the current flowing through this capacitor. So corresponding voltage is V1. So V1 omega C plus I1 is the current flowing through the shunt branch. So you have to consider the effect of voltage over here. So it is taken as V1, EV1, K omega C. So the shunt capacitance value is taken as K into C. Now you just simplify, take omega C common. So V1 plus V2 equal to V1 plus K. So just take V1 common, V2 equal to V1 into 1 plus K. So we know the value of K, it's given as 0.11. So V1 into 1 plus 0.11. So now just we have found out as V2 equal to 1.11 V1. We have calculated V2 as 1.11 V1. Now we are going to calculate what is the voltage across the, we have to apply KCL at junction B. So at junction B, apply KCL. So junction B is here. Apply your KCL. So capital I3 is equal to capital I2 plus small I2. Right? So now again you have to write current in terms of voltage. So I3 is the current flowing through this branch. So it is given by corresponding voltage is V3. So V3 omega C is equal to I2 is over here, current flowing through this middle capacitor. So you will be considering I2 in terms of voltage. So it is V2 omega C plus. The important thing while considering the effect of shunt capacitance, so shunt capacitance branch is over here. It is connected through the tower. So the voltage distribution will be taking up to the top point. So if you are considering for I2, it is V1 plus V2 into K omega C. So now as usual, take omega C common and cancel it out. V3 equal to V2 plus V1 plus V2 into K. Now just simplify V2 plus V1K plus V2K. Now we know the value of V2 already, which is 1.11 V1. Substitute here, V2 plus V1 is 1.11 V1 plus V1 into K plus 1.11 V1 into K. Right? We have just substituted the value in terms of V2 in terms of V1. If you simplify this, you will get V3 is equal to 1.342 into V1. Now we have found out voltage distribution across the third string, insulator string, which is V3. V2 we already found out. Now what is the total voltage across the string? What is the total voltage across the string? So its total voltage is equal to V1 plus V2 plus V3. V1 is already known. V2 is in terms of V1. So 1.11 V1 plus V3 also in terms of V1. So 1.342 V1. So now just you have reduced the parameters into single parameter, the total voltage in terms of V1. If you simplify this, you will get, we know the value of total voltage, it is 19.05 kV. (3.452) in terms of V1. From this, V1 can be calculated as 19.05 kV divided by 3.45. If you solve this, you will get V1 as 5.52 kV. So second one, if you substitute the value of V1 in this equation, you will get V2. V2 is given as 1.11 times of V1. 1.11 into 5.52. If you calculate this, the V2 is calculated as 6.13 kV. Now V1, V2 is known. Substitute here. What's your expression for V3? V3 is given by 1.342. So we have already derived. So V2 also in terms of V1, V3 also in terms of V1. So we know the value of V1. Substitute here. 1.342 into V1 is 5.52 kV. So now V3 is calculated as 7.4 kilovolt. Now we have calculated all the values. V1 as 5.52, V2 as 6.13 kV, and V3 as 7.4 kV. So now from this expression, from this solution itself, we can conclude that the voltage across the last disc, which is nearer to the conductor, is having higher stress. You can see the values. V1 is 5.5 and V2 is 6.13 and V3 is 7.4. So which is under higher stress. Now we are going to calculate what is the string efficiency. What's our formula? It's given by string efficiency is equal to total voltage. So total voltage is 19.05 divided by number of discs. So in this problem we have 3 insulator discs. So number of discs is 3 into voltage across the disc nearer to the conductor. So nearer to the conductor is V3. So substitute the voltage V3, which is 7.4. So from this expression we are calculating the efficiency as 85.5%. So this is our string efficiency. Clear? So what's our problem? It's given with voltage distribution across the strings. We have to calculate. They are given with the problem as 33 kV system and number of discs is 3. They are given with K value as shunt capacitance to the ratio of self capacitance as 11% in the question, and the total voltage is given. The requirement is voltage distribution across 3 strings and finally the string efficiency. So we have just go with the string diagram and we have just marked the voltage across each string V1, V2, V3 and assumed the self capacitance value as C and shunt capacitance as K into C. So K value is given in the problem as 11%. So substitute, and first procedure you have to apply KCL at each junction. Apply the KCL, write your current equation in terms of voltage. So I is in terms of V omega C. So we will be simplifying and get the parameters V1, V2, V3. So for calculation point of view, calculate V2 in terms of V1, V3 in terms of V1, and the total voltage is given by V equal to V1 plus V2 plus V3. Substitute and get the unknown parameter V1 and substitute in the subsequent equations, you will get V2 and V3. So from the solution, we have concluded that voltage distribution across the third string is under higher electric stress since the voltage is 7.4. So from this, we are calculating string efficiency. It's given by the ratio of total voltage across the string divided by number of discs into voltage across the disc nearer to the conductor. So total voltage is 19.05, number of discs is 3 and voltage across the last disc nearer to the conductor is 7.4. If you substitute, you are getting 85.5%. So this is our solution for this problem. So thank you.